Welcome guys. I am so sorry for the long delay. I had some work, so we will now start with kind of new series where we'll continue with the reactions basically throughout the organic chemistry of class 12th and 11th also. So before going into the reactions part, so I need you to understand some part of the if when you take reaction, we will not only study reactions, right? We will study their mechanisms also wherever it is needed. So for the mechanisms, basic terms and basic concepts are required to understand the mechanisms and stuffs. So basically I introduced you to the organic reaction mechanism. Before this, I am not teaching it as a whole lesson at all, from the basics. Of course I'm going to the basics only, but before this, the GOC part and the isomerism part, little bit you should know actually. So maybe in after this series, we will start with from basics or from GOC only. So let us go into the organic reaction mechanism part. So we'll just see some basic terms and concepts in the reaction mechanism part. So if you take this is the basic thumb rule, okay? Understand this for the whole of organic chemistry, for whole of chemistry only. Energy is inversely proportional to stability, okay? This point you get it. It means what? If the energy of a system is very high, okay? Energy is high means the molecules in the reaction are active, like that you can say. So if they are active, what they will do? Will they sit in a place and do something? No, right? They will just move around and collide with each other. They will be so unstable, right? So you can consider humans only. Humans also do the same, right? If you have a lot of energy, for example, you wake fresh in the morning and you will have a lot of energy. You will not be idle. You have to go to jogging, or you will read at the morning time. So like that, so the molecules also behave in the same way. So if the energy content of the system is very high, the stability of the system decreases actually. Stability energy, in a sense, you can consider net energy, or neglecting the kinetic energy, you can consider only potential energy also. So basically this energy is inversely proportional to stability. This point is the most important point of chemistry. Understand this. And hoping that in your class 11th, the thermodynamics part and the equilibrium part you should have studied, at least basics, and you should know what is enthalpy, entropy, Gibbs free energy and all. So if you take there only you should have studied this. If you take this delta H is what? A change in enthalpy of the system. Means nothing but the difference in energy, okay, of the system. For example, if you take a reactant goes into products, so the delta H is defined as the individual energy of products minus individual energy of reactants, okay? So this delta H, if the delta H of the system only, okay, the system, if it is less than 0, okay, it is as a numerical value, right? If it is some negative 1.5, like that, if it is there, then we say the reaction actually is exothermic reaction. Okay, exothermic means what? Exo means outside, thermic means you can say something related to heat. So what happens? Exothermic means the heat is released out during the process, okay? Heat is released, or you can say energy is released, okay? That's what the basic idea. Energy is released means, for example, if some reactant is here, reactants goes to products, okay? If this reactant is for example 1, imagine this 1, okay, unit and all you don't see, only the value you see 1, and the products, if you see, it will be 0.5, okay? So numerically you see this. So what is the delta H for this reaction? Numerically only, I said, right, the energy content of this minus this one, so it will be 0.5 minus 1, which is equal to minus 0.5. See, the value is coming negative. Means what I said, the product energy is decreasing from the reactant to the product. The energy is getting decreased, And where does the remaining energy go? Of course, we cannot violate the law of energy conservation, right? Energy can neither be created nor be destroyed, okay? At least during like our 12th standard discussion up to our level, okay, it is almost true only. Consider it as true only, okay? So where does the remaining energy go? It is it is released as heat, basically. That's what I said. So if heat is released here, this is the symbol for heat, okay? So this means this enthalpy of the system is exothermic. If, for example, the same delta H of system is greater than 0, okay, then this process is endothermic. Endothermic means the heat should be, you can say, supplied, okay? For example, same thing, if R goes to products, you can say this heat, consider this, like if the reactant has energy content of for example 1 only you take, so then the product should be for example it will be of 2 numerically, you think like this. So like where did the extra energy come for the product side? You should supply here some heat, okay? Heat or in some form of energy you should supply, okay? That's why the energy of the product side is increasing. So this kind of process is called endothermic reaction. Remember this, I said this energy is inversely proportional to stability. That's correct. Which means what? I mean, and one more important thing is every system. Wait. So every system requires stability. This is also an important thumb rule. Okay, these three are basically important thumb rule for chemistry. So every system, of course, right? Take for example of humans only. You love to always run, or you love to sit like continuously for an hour. Obviously, like you would love to sit in a place, okay, which means you're stable enough and your energy content is very, very low. It means molecules also behaves in the same way. Every system should go to stability. It should attain stability means what? Its energy should be very, 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 very low, correct? If its energy is low, then stability will be more. Yeah, if its energy is high, it will run like anything and jog like anything. The molecules also same way as humans. So what I'm saying, in chemistry, every system should require stability. Like it's not mandatory, but every system, like it wishes to go to stability, okay, stable part. So if the stability is higher for the system, the energy content should decrease, correct? Because the proportionality we saw here. So basically then here if you see, the reactant side energy is more or product side is more? Reactant side is more, right? So like you can say, what did I say just now? Energy should be decreased so that stability is increased. Here which side's energy is decreasing? Here only, right? So you know the equilibrium will favor more towards the product side. That's what I'm trying to say, okay? The equilibrium favors more the product side than the reactant side in case of a exothermic reaction, okay? So this is basically the rule. In endothermic reaction, the opposite happens. The energy content of the system of the reactant is high, so the equilibrium mostly tends to shift towards forward, okay? This is the basic rules of chemistry, okay? Energy, stability, proportionality, and the delta H of the systems, and stability. Every system requires stability. This is the basic 3 rules of chemistry, okay? Like this is not involved only in reaction mechanism chapter, but everywhere in chemistry, okay? So now we'll see what is actually, like till now I've told about all these rules, basic rules and all. What is basically mechanism? We'll see now, okay? What is a reaction mechanism? Okay, generally if we speak, when some reactant goes to products, okay, you cannot say every time that you have a compound A, you do something to the reaction, you add something to the reaction, or you give heat, whatever, it suddenly transforms into products. That is the that happens only through that only you see your nude eye, okay, your naked eye. What actually happens, we can't see that, okay? So for understanding what happens in the reaction, scientists give a basic pathway to the steps and the process which is happening while the conversion of reactants to products, okay? Basically this mechanism is not happening exactly, okay? Something is happening here to prove that scientists give mechanisms. Okay, fortunately you need not derive the mechanisms and all. You're studying 12th only, so when you go deeper into study of chemistry, you will do that. Okay, so already scientists gave many mechanisms. Okay, you cannot just like that you cannot give mechanisms. It should follow every rule of chemistry. Okay, like stability rule, energy rule, every rule should follow. You'll slowly see. Okay, so that is the basic rule. The pathways where a reactant is converted into products, that there can be one single way, like directly can get converted. I'm not saying it will not happen. Okay, it can directly be converted to a product in a single way, or it can take 2 ways, or it can take also 10 ways. Okay, this is not exactly like happening. That means we cannot say that this is only happening like 100%. We cannot be sure, because it is difficult to look into that, because basically these organic reactions, I mean, like generally reactions are very fast. Okay, like at least for the steps I'm saying, right? If for example for this reaction, for example, it took three steps to to get converted into products. The 3 steps will be like very fast. Okay, so that's why we are not able to, like, mostly we will not be able to see. But what happens, scientists prove this pathway, like by giving certain mechanisms and all. Okay, this might have happened, this could have happened, like that. Okay, this pathways, and we studied it as mechanisms. Okay, that is what mechanism means. Generally in mechanism you can see these basic terms. Okay, where one is called transition state. Okay, transition state is nothing but, for example a reactant is getting converted into products. Okay, I said, for example, it is taking single step only. Okay, it is getting converted into single step, consider like that. Okay, what happens, for example, here this is consider this as energy. Okay, consider this to be energy. Okay, this is x-axis, y-axis, this is energy. Okay, and this is the progress of reaction. Progress means how far the reaction has gone. Okay, like that, progress of reaction. Okay, for example, I'm saying this is the reactant. Okay, this is going like this. Okay, this pathway, I mean the path is going like this. Okay, like for example, the reactant is here, slowly the energy of the system is getting increased, and it reaches a peak here, and suddenly the energy of the system is getting decreased, and it is getting more decreased, such that it is going to down level when compared to the reactants. Okay, it is going, see, it is going below this line, right? So this is what it is trying to say. Consider this reaction to happen here. It is increasing, keep on increasing, and it attains a certain state, and it finally starts to decrease. Okay, this state maybe it can be called as a transition state. Okay, transition state, remember this, transition state is of higher energy. Okay, higher energy. This transition state you cannot see. Okay, you cannot even, like, it is very like it is to form this transition state only, it is getting very less time, and the transition state will not even exist. Like, you cannot think of the number itself, very few nanoseconds. Okay, the transition state will not exist. Okay, it will not exist only. Then why should we study about the transition state? This is a good question. If you have this question in your mind, keep this question as such. We will see in the reaction mechanism, like one by one. There I will say why transition state is important. Why should we study about the transition state? Okay, now this you leave. Okay, next, if you take intermediate. Okay, intermediate, if you take, this is also of higher energy only, but not of a transition state. Consider another reaction, like same way, but what is happening? It is going like this, and like this, and like this. Okay, what can I observe here? Okay, the reactant is like maybe like this. Okay, the reactant is here, it is of some energy, it goes up to this transition state. Okay, and suddenly decreases up to some platform here. Okay, here, and again suddenly the energy increases, goes to another transition state, and suddenly decreases, which is lesser than the reactants also. What this means? Okay, this intermediate, it is also like similar to transition, okay. Both are not same, okay. Do not confuse these both, okay. These are not same, somewhat similar you can say. Intermediate also you cannot separate easily, but you can in some cases, but you can't separate easily in, like as you think, okay. But intermediate exists little more time than this transition state, okay. And then you can say, and again you can ask, why are we studying intermediates, okay. Intermediates are of more types. Next part we will see about nucleophiles, electrophiles and nucleophiles. There I'll say about intermediate, some idea I'll give, and then we will see the reaction mechanisms. I'll say more about intermediates, okay. Intermediates can be carbocation, example I'm saying carbanion, okay. These intermediates are involved in the reactions. Why are we studying this? If that I'll say in the reactions part, and maybe I'll give you a basic idea. Like if you know which intermediate is getting formed, based on that you can judge the stereochemistry. You can you can change the reaction, you can control the reaction using that, okay. You can say that we cannot even see the intermediate, how can we control the reaction? That's what I am saying, we can study in the reactions part, okay. For now this is the basic terms and reaction mechanisms, okay. And I said, right, like for to achieve this transition state here, some energy is given here, right. That energy is basically called the activation energy, which you should have studied in chemical kinetics in the Arrhenius theory, okay. Under that you will study, you should have studied that. So that is called the energy of activation. That's simple term, you just know that. More detail of that you will study in chemical kinetics if you haven't studied it, okay. So next we will see about electrophiles and nucleophiles, okay. What is electrophile, what is nucleophile? So we'll now talk about electrophiles and nucleophiles in general, basically. So like I told you, right, for the basics of getting into some reactions of general types like substitution, addition, elimination, you need to know like some kind of basics, okay. So if you take electrophile, okay, so if you take electrophile, phile means what? Phile means lover, okay, like it means love, okay. Phile refers to love. So electrophile means it means electron lover, okay. So like it needs electron, okay, it loves electron, so it is called electrophile basically. So electron is negatively charged species. So which compound will need a negatively charged species? A positively charged species. So we generally represent electrophiles as E plus, okay. So this is electron lover. So this is basically, and the opposite is nucleophile. Nucleophile, this is just my representation, you can represent it as you wish, okay. So this is my sorry. So the nucleophiles means it's nucleus lover. Nucleus means what is their nucleus actually? Mainly it consists of proton. So proton lover means positive charge lover. So you can consider the negative charge in this representation. So this should be proton lover. For example, okay, you can write it as nucleus lover, okay. So this is the basic definition you can say for electrophiles and nucleophiles. So if you take some examples you can consider for this. So for example we'll take some ions, okay. So ions means positively charged or negatively charged. In this case it's positively charged, okay. So if you take ions, generally positive charged means, positive charge means what? They are cations, right? Sorry, so they are cations. So in the ions case cations are the electrophiles. And similarly if you take some reaction intermediates, okay, like reaction intermediates are nothing but we'll see in more detail when we see reactions. I'll just say for now, reaction intermediates are some kind of species which like involve in the reaction, okay. For example, if you convert a reactant A to a product B, you will get some intermediate in this reaction which you cannot separate it 99%, okay. You cannot take it out separately and show this is the intermediate. It will be formed in situ, okay. In situ means it means it forms inside the reaction itself, and it is not like available, I mean you cannot separate it out of the reaction. Very rarely it is separable, okay. So reaction intermediates means that is the reaction, that these are known as reaction intermediates, okay. So reaction intermediates, okay. So I'll say further about this example of these, like when we see reactions. But for now, I'll say just it is you can take carbocation, okay, carbocation. You can take a free radical also. And you can take carbene. This you'll study in detail, okay, while we come to reactions part. Okay, these are the examples you can take. And when you take neutral molecules, okay, neutral molecules can also be electron lover. Why it's it like that? Okay, I'll say. So if the molecule is neutral, okay, actually it doesn't mean that it is like full of valency filled. For example, I'll say, wait, if you take fluorine molecule, okay, fluorine atom, it is not having its octet complete, right? But still it needs electron. But does it have any charge? No, because the proton and the number of proton, number of electrons are equal. Thus fluorine has no charge, but it still needs electron. Okay, so neutral molecule can also be example for this. Okay, for example, but I just said fluorine as an example, not it will not like come in this case, because I'll save it. So if you take a neutral molecules, it will you can consider this. You studied in chemical bonding, right? Odd electron species like AlCl3, BF3. These are like incomplete octet. It will have only sextet of electrons. Sextet means 6 electrons, okay, in this central atom. So this neutral molecule, but due to the fact that it has only 6 electrons, it needs 2 more electrons to get octet complete, right? So this means also this is electropositive only, means electron lover only. So you can consider a neutral molecule also to be electrophile, okay. So this basically all these has vacancy for electron to fill in it, okay. So that is why they are known as electrophiles. If you remember, okay, in chemical bonding we have okay, not in chemical bonding exactly, in equilibrium chapter, while we studied you should have studied the acid base theories, where you studied Lewis theory of acids and bases. Lewis acid says what? Lewis acid means it is acceptor of electron. That is what Lewis acid means, right? Okay, so basically that is here. So you can call, if you found, you can call it as Lewis acid also, okay. There is nothing wrong. Lewis acid, okay. Pardon my handwriting, please. Okay. If you don't understand anything, you can ask in the comment section below, okay. So this is Lewis acid. So this is over here, okay. And similarly, if you see, you take for nucleophiles also. So if similarly you can just pause the video and try it out. It's simple, okay. So ions, if it is cations for this one, it will be anions. You know these cations means positively charged species, like for example H plus, and what else you can say? You can say for example NH4 plus, H plus, so like that. So if you take ions, and anions means you can take OH minus, Cl minus, etc, etc. And similarly reaction intermediates, if you take, it will be what? Like just guess. If it is carbocation, this will be carbanion. These details I'll tell you like later in the reactions. So this is reaction intermediates. And similarly neutral molecules can also be nucleophiles. For example, if you take like here you saw like the central atom does not did not have electrons, so it is getting electrons. That's why they are categorized under electrophiles. For nucleophiles, it already has electrons, but remember this is neutral, it does not have charge. How? I'll say. So if you take H2O for example, H2O has 2 lone pairs of electrons on oxygen, right? So these 2 lone pairs of electrons can be donated. For example, this can be donated to some proton like H plus to form H3O plus, okay. It's a hydronium ion. And you can also take NH3. These examples, okay. So and one more class of compounds come here, which are known as organometallic compounds. Organometallic compounds. So what are these? Okay, basically if you split the word, and you can see organic means it should have a carbon, okay, and metallic means it should have a metal in it. So and for example, if you take RMGX, this is a famous reagent. Remember throughout your JEE preparation or whatever, if you remember throughout your life also, no problem, there is no loss in it. So if you take RMGX, it is known as the Grignard reagent. See, R is the carbon part, it can be anything, CH3, CH2, anything. Mg is the magnesium part, which is a metal, okay, basically, and X is halogen. This you leave. Like generally it consists of a metal and organic part, okay. So RMGX you can take, and R2CuLa you can take. So like this you can take. So you can say, okay, how this can act as nucleophile. Basically this is not like existing as a single compound. Basically what happens, right, Mg actually it can give away 2 electrons, right, it can exist as Mg2 plus. In Mg2 plus, 1 electron is given to like this halogen, and one is given to this one. So it will exist actually like this, R minus and plus 2 and minus. So this is minus 1 minus 1 minus 2 plus 2 0. So hence the molecule is neutral. So so in this case, this will actually be like donated. It actually donates R minus, okay, for any reaction. We'll see the reactions later. It has a lot of reactions involving Grignard reagent. You can prepare anything. It is like easy, like it's the king of, I can say, organic chemistry. So R minus you can take and react it with alcohol or water also sometimes, and sometimes carbonyl compounds like aldehyde ketone. So this can basically donate the electrons, okay. These are what I know, like, and similarly you can call this Lewis base if you want. So basically what these electrophiles and nucleophiles combine together, okay. I'll say how. For example, if you take H2O, if you take H2O is what I said, this is a nucleophile, and if you take H plus is what, it is like a cation basically. So it is a proton, okay. What happens here, this is a deficient of electron, it has more electrons, so it will give this electrons here, okay. This is the rule of chemistry, like only the arrow mark should be drawn from the place where electrons are more, okay. So here electrons are more, so electrons are given from here to here, okay. So it will be H2O, it gives here, okay. So what will happen, if it donates a pair of electrons here, it will get a plus charge, okay. That's the basic rule. Okay, can you get it? Because whenever we like you have studied, right, when for example sodium, when it loses electron, it becomes sodium plus Na positive. Similarly H2O, when it loses electrons, a positive charge is gained, okay. But what happens, this pair of electrons comes and bonds itself to H plus. I'll say how. So like this will happen. This is not exact, I'm saying just to understand, okay. So this is H2O, right. So these are two pairs of lone pairs, okay. So now this will come and abstract a proton, okay. What will happen, it is already having a positive charge, means it is having a vacant p orbital, s orbital here, okay. So what will happen, this will come here. So what will happen, H O, and this lone pair will remain as such, and H will come, and these two electrons forms a new bond. This is the key concept of reaction mechanism basically. What will happen so like whenever electrons are donated, a pair of electrons are donated, it forms a new bond, okay. You have to remember this concept forever, okay. New bond is formed, and sometimes like here it is donating electron from oxygen. Sometimes bond can also be broken, like for example this bond can break, and these pair of electrons can go and attack H plus. I'm not saying this case, okay. Generally I'm saying this can happen. Here it is happening like this, these electrons goes and abstracts the proton, okay. Generally a bond can also break. So in general, when we conclude, what will happen, bonds break and bonds also form, and that is how a reaction occurs, okay. It occurs like that only. We'll see slowly. So what will happen, this new bond is formed, okay. Just highlight it more. New bond is formed, and here it will be, and to show this electron, like it is shared between this oxygen and the hydrogen, right? So you'll get a positive charge here. So basically you should have read a formal charge concept, okay, in your covalent chemical bonding chapter. There you can find you find what, like they'll give a molecule and ask you to like find the charge on the element, okay. So if they give H3O only they give H3O, okay, and like they are asking you to find the charge on oxygen, you'll use the method, okay, the formal charge method, to find the charge on oxygen. So you'll get it as +1, okay. Basically, if you don't know how to find formal charge, I'll upload a video on it, no problem. Or else you just revise chemical bonding will come, okay. So this is what actually, this is a nucleophile, this is an electrophile. This both combines to form a reaction, or basically you can say Lewis acid and Lewis base combine to form a reaction. Lewis acids are electron acceptor, and Lewis bases are electron donor, and remember this forever, okay. So like this is known as this is the basic concept of a reaction mechanism, okay. So this is about electrophiles and nucleophiles. Next we'll go and see about nucleophilicity and basicity.